Hey everybody, in this video we are going to do a formal introduction. My dog and I, Dallas. We're going to do a formal introduction to solving trig equations, and we're just going to start, I'm going to call it 1.01. So the first one is involving only one trig function. So in this example you see on the screen now, it's only sine theta. It's not a mixture of sine theta and cosine theta or anything like that. And then what we're going to do is we're going to find all solutions, which is the 0.01. When we find specific solutions, that's going to be like 0.02. All right, so you'll see that in a future video. So this is a very, very straightforward situation. So I just want to kind of dive into one clean-cut example. So let's look at that. Here we have, how do you know, for starters, how do you know that it wants you to find all solutions or a general formula? The way you figure that out is in the directions. So here the directions just say solve 2 sine theta minus 1 equals 0. There are no other details indicating anything about a specific window of answers to be looking at. Oh, I want all the answers that are from here to here, or, you know, find me all customers who purchased this sneaker in the tri-state area in a size whatever. So you can narrow things down. Now, the frame I have around this desk camera right now, it's all wavy, and that is on purpose. It's relating to trigonometry. And the thing about trigonometry and the unit circle is it's a periodic function, right? Your answers repeat over and over and over. So we're going to have an infinite number of solutions to this equation. So because it doesn't specify, find me the answers between this and this, we're going to have to figure out a way to write an answer so that we're encompassing all of the answers without trying to write all of the answers, because that's an impossible task, okay? How do we get started? Well, when it says solve, we're always solving for a variable. Hopefully we all know that. That is what algebra taught us, right? In algebra, we used x. In trigonometry, we tend to lean more towards theta. Maybe your teacher uses x instead of theta, okay? I'm a fan of theta. So we want to solve for theta. That means we're going to be applying what we call inverse operations. Most people, when they think about operations like add, subtract, multiply, divide, they want to go in the order of operations, like the PEMDAS order of operations. But when you're solving for x, you're kind of peeling off layers. You're almost going in the reverse order a lot of the time. So in this situation, remember, we're peeling off layers. We want to get sine of theta alone first. Then from there, we're able to get theta alone. So the first thing we're going to do is I'm going to go ahead and I'm going to add 1 to both sides, because what we do to one side, we do to the other. The equal sign acts as a fulcrum of a seesaw or a scale, and it keeps balance on both sides, right? So if I add 1 here, right, that's gone. And then here, 0 plus 1, well, that just becomes 1. Remember, it's not like you're adding 1 here and subtracting 1 here. That would make no sense, right? That's having a balanced seesaw, adding a pound on one side, taking a pound off another side. Now there's a 2-pound difference. Like, what are you doing, you know? So what do we have? We have 2 times the sine of theta, almost like the square root of x, or the log of p, whatever it is. So whatever the function is, in this case it's sine, we're taking sine of x or theta. So again, that's like saying the square root of x. It's an operation, a function operation being applied to, in this case, our variable. And that is equal to 1. Next layer to peel off is the multiplication. This 2 is attached to the sine theta with multiplication. So the inverse operation of multiplication is division. So this 2 and this 2 are going to divide. Now here, with adding and subtracting, you want to get what we call the additive identity, which is 0. When it comes to multiplication and division, what we want to get is something called the multiplicative identity, which is 1. So when you multiply or divide, to get rid of something, you're really getting rid of it by leaving a 1 behind, because 1 times anything is okay. And then adding 0 to anything is also okay. Now that leaves us with really the nitty gritty. Sine theta equals 1/2. So at the bones of this problem, right, we want to know, not in general, should avoid the word general. We're not just broadly looking for 2 sine theta minus 1, when does that equal 0, but more at the core of it, we want to know, well, in that case, at what angle or angles does the sine of theta, in other words, the y value on the unit circle, at what angles will the y value on the unit circle equal 1/2? Now, a lot of people in this situation, because you should know this by heart, you're going to be able to just jump to it and be like, oh, when theta equals this, when theta equals that, when theta is this, that, whatever. And you're going to be able to rattle off your answers. And that's great. I'm happy for you. What do you do when it's not on the unit circle, right? If it's not on the unit circle, we need help. That help comes in the form of your calculator. Amazing. So how do you get rid of sine theta? We still have to peel that layer off, right? We've been using inverse operations. For the -1, we use +1. For the times 2, we use divide by 2. So what is the inverse of the sine of something? So remember, if I were solving for x here, right, and it was like square root of x equals 4, and I asked you, how do you get x alone? You better not tell me, just divide by square root. No, don't do that. Don't do that. That's so silly. That makes no sense, right? You can't, that's not a thing, right? How do you get rid of a square root, right? Well, we get rid of a square root by applying the inverse operation. What is the inverse operation? What is the edit undo, right? Control Z, Command Z of a square root? That would be to square, or to raise to the second power. And in that case, the square and the square root, bye-bye. Right? They get rid of one another. They knock each other out. And then you're just left with x equals 16 in a case like that, right? Well, what is the inverse operation of sine? No, it's not cosine. Try again. What's the inverse operation of sine? No, it's not cosecant. Try again. Cosine is a cofunction of sine, not an inverse. Cosecant is a reciprocal of sine, still not an inverse. Well, the inverse of sine is, so I'm just going to kind of put us back here. My dog is sniffing around, sorry. The inverse of sine is to take the sine inverse, just like that. So sine inverse, mathematicians, I guess we got a little lazy, right? So ran out of creative ways to name stuff. So we're just going to call the inverse of each trig function, sine, cosine, tangent, cosecant, secant, cotangent, the same name, and the word inverse at the end. So that was like if we travel back in time and we just called it addition, addition inverse, multiplication, multiplication inverse, squaring, squaring inverse, okay? So think of it a little bit that way. So if I take the sine inverse, if you could see my dog climbing on the desk right now, why can't you help? You're not being helpful. Like, take the pen and do a little work, no? Okay. So the sine and sine inverse right here in this spot are going to go bye-bye, okay? I don't want to use the word cancel because, again, the word cancel means 0. So they just get rid of each other, right? The composition of inverses with one another leaves behind an x. That's a conversation for another day. Perhaps you already know that from a prior lesson, right? So what's left is just theta, and that's beautiful. And then how do you read this sine inverse of 1/2? How do you read that as a question, right? Well, that's saying to you that the sine of what angle, and really angles is equal to 1/2. So it's like when you first started doing square root, right? Or, yeah, I guess it would be more like square root. And you say you were teaching, he's on the desk. And when you were first learning square root, how did you explain the square root to a small child, right? What number times itself is equal to 25, you know? You couldn't really phrase that in any fewer words, right? It was kind of a mouthful. Well, same is true of sine inverse, same is true of log, right? How did you read when you were looking for, 2 to the x equals 8? You might be able to ask yourself the question, 2 to what power is 8? But what does that look like as log for cases when it's like 2 to what power is 81, right? Well, that would be log base 2, 81 in the calculator. And that is going to find the x for you. Well, someone might just see the bottom thing and be like, log 2, 81. No. That's not how you read it. Log base 2 of 81, or 2 to what power is 81. So a lot of these inverses are kind of a mouthful. Got it? So now, like I said, you're often going to be able to kind of skip these 2 steps right over here, because if it's something that you can do with your brain pretty quickly, with your knowledge of the unit circle, you're really not going to have to show these steps. These steps are sort of reserved for the cases where I'm going to find the sine inverse of like 2/3. That's not on the unit circle. I'm going to need my calculator to help me. And that's a whole other conversation, okay? Because calculator is a function tool. It's only giving you one answer in one quadrant. You're going to have to apply it and figure out what other quadrant it would have an answer in. Figure out that answer and then decide, do you need a general formula, a general solution, or are you just looking for a couple answers? What's going on? So, a whole bunch going on. So like I said, we're going to skip these 2 normally, and you're really going to be able to just sort of go from this right here to theta equals whatever, theta equals blank. So where is sine equal to 1/2? Well, here's a little cutie unit circle for us. And up here we see xy, cosine and sine. Really, I guess I should say theta, because x is x in this case. So it's not really nice that I have x's there, but I digress. The y value is sine. And I want to know, when is the y value on the unit circle equal to positive 1/2? Well, the y value is positive going up from the origin, or in this case, up from the y-axis. So up 1/2 is up just that little bit right there. Where else is it up just a little bit? Oh, right here. What angles correspond to those scenarios? The angles that correspond are pi over 6 and 5 pi over 6. Now, again, we need infinite solutions. We need all of it, a general formula. So by me writing theta equals pi over 6 and theta equals 5 pi over 6, I'm really not finding anywhere close to all of the answers. I found two, go me, that's great, but like there's infinite. So that's definitely not all of them, So what else? Where else does sine equal 1/2? It looks like it's just there and there. Well, remember, periodic, cyclic, that same pattern over and over and over and over and over again. But it's periodic in the sense that it reoccurs the same distance apart over and over and over and over. 12 noon happens at the same time every day, So how do I figure out every other angle that lands at pi over 6, or all of the coterminal angles for pi over 6? And how do I figure out all of the terminal angles at coterminal at 5 pi over 6? Well, I need to add a full loop, or, subtract one, adding a negative. Okay, let's do that in the nicest way possible. So let me move that out of the way. So my first one was theta equals pi over 6. And what I'm going to say is I'm going to say plus, now a full loop, a full revolution is 2 pi radians. I'm going to add 2 pi. Now, do I have to add it? I don't have to. Could I add it once? Could I add it twice? 3 times, 4 times, 5 times? Could I subtract it? All of those, yes. Could I add half of it? No. I need a full amount of 2 pi to be added or subtracted or not to pi over 6. So I'm going to write 2 pi times n. That's going to indicate the number of times we're adding 2 pi. And if I make n negative, I'm just subtracting it. Or if n is 0, I'm not doing anything. Comma, where n is an element in the set of integers. So that symbol right there means it's an element. And then this is element in. And then this right here means the set of integers. Integers are numbers like -2, -1, -3, 0, 1, 2, 3, 4, 5. Those are integers. So we're not getting parts of numbers. We're only getting whole amounts of numbers. Now, if I write this once on top of my paper for a certain assignment, I might say like for all uses of n on this worksheet, n is an element in the set of integers. Once you imply it once and make sure you apply it to your whole assignment, you don't have to keep writing it. If you want to write it every time, go crazy. So that is one general solution or a general formula. And the other, all you do is that same thing, 5 pi over 6, because I can't hit both of them with one formula, because if I'm going from pi over 6 to 5 pi over 6, that's 4 pi over 6 apart. And then I loop around and hit where pi over 6 is again, that would be at 13 pi over 6. So 5 to 13, that means I'm adding 8 pi over 6 this time. And then I'm adding 4 pi over 6 again. And then I'm adding 8 pi over 6 and then 4. You can't write a formula that's like go 4 hours and then 8 hours, 4 hours and 8 hours. You could set a timer that goes every 4 hours. You could set a timer that goes every 8 hours. You're not really setting a timer that oscillates between those two things, you know? So I'm just going to write it again. And there you have it. So this is a Z with like an extra line in it. And I always cross the Z's because a lot of you guys make your Z's that look like 2's. I'm not a fan. All right. And this over here, final, let's even write the word final answers. Okay. So that right there, that represents our final answers to this example. So I just went heavy into it. I could add a little bit of a picture, so you just have that on the screen again. So right there is your 5 pi over 6, right? And over here is your pi over 6. That's where they land. Obviously, if you did it in degrees, you would write 30 degrees, and instead of 2 pi, you'd write 360. And you would write 150 degrees, and instead of 2 pi, you would write 360n, okay? One last sneak peek, bonus footage is, let's show you, okay, okay, so I don't know if this is going to be dusty or what, but okay. I have my calculator over here and I put it into radians, okay? Second quit. All right, I'm on the main screen. If I did sine inverse, it's right there. Oh, you can't see it. It's right there. I think I have to hit it twice. Yes, if I hit it twice on this calculator, it pops up. So if I did the sine inverse of 1 over 2, I mentioned before, a calculator is essentially a function tool. It's not a computer. It spits out one answer, okay? It's not that smart. You are smarter, believe it or not, than your calculator, you know? So if I hit enter, it's in radians. So this is going to be like a whole wackadoodle thing. It's telling me this. What the heck is that? Well, for starters, it's not going to give you your answers in terms of pi. Maybe if you have a nicer calculator, it can do that. Some do, in fact, do that. But just to show you for sure, if I go over here and I don't use this often, so if I'm struggling to find a button, forgive me, pi divided by 6, right? So think about it. Pi is 3.14 divided by 6. Well, 3 over 6 is a half, 0.5. So 3.14 divided by 6 should be a little bit more than a half, which is a little bit more than 0.5. And let's find it out. Bam, there you go. Now, the other issue is that number, 0.523598776, is approximate because it's rounded. Pi is an irrational number, non-terminating, non-repeating. By writing our answers in terms of pi, we are significantly more precise, but it didn't give me the other answer. It doesn't tell me 5 pi over 6, but that's why, you know, we're smart. And we say to ourselves, sine is positive a half. What other quadrant, is sine positive 1/2 in? Oh yeah, quadrant 2. Well, how do I end up with that same reference angle that this gave me? This gave me an angle in quadrant 1. That's a reference angle right there. I need to find one in quadrant 2. So what I would do is I would go in and do pi minus, and then I would subtract the decimal from before. And it's going to get me at that pi and scooch up pi over 6 or 0.5 blah, blah, blah. So if I subtract, I get this bad boy. Guess who that is? Let's double check. 5 pi divided by 6. Enter. There you go. So that's a little sneak peek at calculator knowledge. And I will have a short part 2 to this where we're going to talk about answers, say, between 0 and 2 pi specifically. And that's it. So I hope you feel very smart right now. You should feel smart right now. We just covered a lot of great information in only 20 minutes. That was like a super lesson. So if you do feel smarter, or if you have anything to add, tell me about it in the comment section underneath. I appreciate that. And any calculator recommendations, put them underneath. People might need one when they go to college. I don't know. And then if you feel pretty good about what we're looking at over here, then you can go ahead and give the video a thumbs up. And if not, well, go ahead and give the video a thumbs down. Okay. So do what you got to do. I won't be offended. And click through for part 2 if it pops up on the screen. I hope you're having a great day, night, week, month. Adios. Dallas, get off the desk. Say bye, everyone. Bye. He doesn't care. His man bun's falling out.